So welcome to the new topic, hydraulic turbines. So in this class we are discussing about hydraulic turbines. So what exactly is a hydraulic turbine? So the definition for hydraulic turbines or hydraulic machines is that it converts hydraulic energy into mechanical energy. So actually hydraulic turbine is the machine which converts hydraulic energy into mechanical energy. If we use the term hydraulic machines, then it consists of turbines and pumps. In the pumps, what happens is that there the hydraulic energy, mechanical energy is get converted to hydraulic energy. But in the case of hydraulic turbine, we are converting hydraulic energy to mechanical energy. So it was developed in the 19th century and it is purely used for the generation of electricity. So this type of turbines, hydraulic turbines, are usually found near the dams for generating electricity. Okay, so the classification of hydraulic turbines, there are a lot of classification regarding hydraulic turbines. So according to the principle of operation, it is classified as reaction turbine and impulse turbine. Lot of other classifications are there, but we in this class we are not discussing about those classifications. We are only discussing about the main classification, that is impulse turbine and reaction turbines. So first of all, I'll look into what exactly is an impulse turbine. So impulse turbine. So impulse turbine is a turbine which converts pressure energy of water into kinetic energy. Here the main principle is that the whole pressure energy of the water gets converted into kinetic energy before striking the turbine blades. So it gets converted into kinetic energy while it passes through a nozzle. So in an impulse turbine, the pressure energy of water is converted into kinetic energy when passed through the nozzle and forms high velocity jet of water. The formed water jet is used for driving the wheel. So the Pelton wheel is an example of impulse turbine. So the name comes after the American engineer Lester Allen Pelton. So the Pelton wheel among the various impulse turbine that have been designed and utilized is by far the important. The Pelton wheel or Pelton turbine is a tangential flow impulse turbine. Since the jet of water striking the wheel tangentially, it is known as tangential flow impulse turbine. So this is the construction of a Pelton wheel. So it consists of a casing. The blue color indicates the casing, and the main component includes a wheel will be there. This is the wheel, and the buckets are arranged over the wheels. Some buckets are arranged over the wheels, and the penstock carries water from the dams to the turbine. So at the end of the penstock, a nozzle is provided. So the function of a nozzle is to convert the pressure energy to high velocity kinetic energy. This high velocity jet of water issuing from the nozzle impinges on the buckets provided over the wheel. So the bucket starts rotating. So the bucket speed can be adjusted by using a spear. Nozzle spear is placed here. So if we adjust this sphere, we can control the flow of water. If we want to stop the water, the spear must be fully closed. That means the spear must completely enclose the opening. Thereby we can stop the water. But what will happen if the water stops? Due to inertia, the wheel continues to rotate. So wheel will continues to rotate. So in order to stop the wheel, we need to provide braking nozzle. So we need to provide a braking nozzle. Thereby we are supplying water in the opposite direction. By supplying water in the opposite direction, we can stop the wheel. So the main function of the casing is to avoid splashing of water. So these are the main components of a Pelton wheel. So the Pelton wheel bucket is a special type of bucket. So it is named as double hemispherical or double hemispherical or double ellipsoidal bucket. These buckets are known as double hemispherical or double ellipsoidal because it consists of two portions uh, divided by a splitter will be here. So there will be a splitter, and the jet of water coming from the nozzle is splitted into two, equally splitted into two. One portion moves in the topmost portion, and the other portion moves downward. So it is actually separating the water into two portion, and the angle of the splitter is decided as 10 degree to 15 degree. So this is the angle of the splitter, so that by providing this angle, the water separates to two portions of the bucket. So L represents the height of the bucket. So this figure is the left side view of the first figure. So this left side, if we view from the left side, the bucket will be shown like this. Bucket will appear like this. So L represents actually the height of the bucket. This portion is fitted over the wheel. This portion is actually fitted over the wheel. So L represents height of the bucket, and B represents the width of the bucket, and D represents the diameter of the jet. D is the diameter of the jet, and this circle represents the jet of water striking at the middle portion of the double hemispherical or double ellipsoidal bucket. So the various dimensions are like this: L by D. So the ratio of height to the diameter of the jet is limited to 2 to 3, and width to diameter of the jet is limited to 3 to 4, and diameter of the D, capital D, represents the diameter of the wheel. So over the wheel we are providing the buckets like this. So D represents the diameter of the wheel, and D by D represents diameter of the wheel to the jet of water, diameter of the jet of water, which is limited to 11 to 16, and T is the thickness of the bucket. So this represents T. So from this portion to this portion represents T. So T divided by diameter of the jet. So all these ratios are taken according to the diameter of the jet, and this ratio is limited to point T by D, limited to 0.8 to 1.2, and the notch width is represents width of the let B is equal to 1.1 D plus 5 mm. 1.1 D plus 5 mm. So like this we are designing a Pelton wheel bucket. So the name of the bucket is, or the shape of the bucket is, a double hemispherical or double ellipsoidal bucket. So let us look into the work done and efficiency of the Pelton. In order to find the work done and efficiency of the Pelton wheel, we need to draw the velocity diagram. So we know that the angle with which the jet strikes the plate is 0 degree. So the jet is striking the plate in this direction, and it is splitted into two. So the angle with which jet strikes the plate is 0 degree. So this jet striking the plate at 0 degree. So V1 represent the absolute velocity of the jet, that is the velocity of the jet issuing from the nozzle, and u1 represents the speed of the bucket, the speed with which bucket is moving, and vr1 represents the relative velocity. is the actual velocity with which the jet strikes the plate. Since the plate is moving with a velocity u, so the jet strikes the plate at a relative velocity only. And Vw1 represents the horizontal component of the absolute velocity of the jet. So Vw1 is equal to V1. For Pelton wheel, Vw1 is equal to V1, and there is no Vf1 term. There is no perpendicular component. So Vf1 is equal to 0. So this is the inlet velocity triangle of the Pelton turbine or impulse turbine. So the alpha is 0 and theta value is 0 here. The exit velocity triangle is similar to all other types of velocity triangle that we had discussed earlier. So there will be a relative velocity term and absolute velocity term, and the vertical component of absolute velocity Vf1 is there, and the horizontal component of absolute velocity Vw2 is there, and the u2 is the peripheral velocity of the bucket at the exit. But in the case of Pelton wheel, the inlet velocity of the bucket, inlet peripheral velocity of the bucket at the inlet and the outlet will be same, and it can be represented as u. Since u1 and u2 are same, we can represent it as u. Okay, this is the velocity triangle. The outlet velocity triangle is very much similar to the that which we had discussed earlier, and the only difference is here that inlet velocity, the angle with which just strike the plate is 0. So all the terms will change. So next we will discuss about the work done terms and the efficiency terms. So here the term Vr1 is equal to V1 minus U1. V1 minus U1. So V1 is this much length is the V1, and that is Ln minus Lm case. The Ln is equal to V1 and Lm is equal to U1. So V1 minus U1 gives Vr1 term. So Vr1 is equal to V1 minus U1. We know that U1 and U2 are same, so V1 minus U. Also, we know that Vw1 is equal to V1. So from the outlet velocity triangle, we need to find the Vr2 term. So first of all, we need to know the Vr2 value of Vr2. So for the Pelton term, Vr2 is taken as K into Vr1. So K is the blade coefficient. K is the blade friction coefficient. So it is actually the value of K is less than unity. Normally it is less than unity, but for ideal buckets, that is if the bucket is perfectly smooth, there is no friction, then K value will be equal to 1. If the bucket is perfectly smooth, then K value is equal to 1. Next we need to find the term Vw2. So we know that for first term we need Vw1 and Vw2. So next we need to find Vw2. So what exactly is Vw2? So Vw2 is equal to Vr2 cos phi. So Vr2 cos phi becomes the horizontal portion. Vr2 cos phi gives the horizontal portion. So minus U2 gives Vw2. So Vr2 cos phi minus U2 is equal to Vr2 cos phi minus U. U2 and U1 is equal to U. So we are taking it as U, and the beta angle is less than 90 degrees. So we are taking it as acute angle. Also, we know that the classification of Pelton wheel or the impulse turbine, so there will be slow runner, medium runner, and faster runner. So if we are deciding whether it is slow runner, medium runner, or faster runner, we need to look into the term beta. So the angle with which the absolute velocity at the outlet makes with the horizontal gives a beta. So if beta is less than 90 degree, if beta value is acute angle, then the runner becomes slow runner. If it is equal to 90 degree, then it is medium runner, and if it is greater than 90 degree, it is known as fast runner. So the force exerted by the jet of water in the direction of motion. So force exerted by the jet of water. We know that if beta is less than 90 degree, Vw2 term becomes negative. So here the term becomes positive. So force exerted by the jet of water in the direction of motion is given as rho a v1 into Vw1 plus Vw2. So the derivation for this term we have already discussed in the earlier videos. So if you want to clarify anything, you can watch that video. So here the rho means the density and A is the area of the jet, which is given as pi by 4 d square. So next we need to find work done by the jet. Work done by the jet on the runner. So work done is equal to force into runner velocity. So due to this force, the runner is moving forward. So force term is rho a v1 into vw1 plus vw2 into u. Work done per second per unit weight of water striking. Next we are going to find work done per second per unit weight of water striking. Per unit weight means mg. M into g gives the unit weight. M is the mass and g is the acceleration due to gravity. So mass term is rho a v1 and g. So dividing the work done term by m into g gives work done per second per unit weight of water striking the plate. So the final equation becomes cancelling this term and this term. The final equation becomes 1 by g into Vw1 plus Vw2 into U. So work done per second per unit weight of water striking the plate is 1 by G into Vw1 plus Vw2 into U. So we know that kinetic energy of the jet per second. Kinetic energy of the jet is normally kinetic energy is equal to half mv square. So m is equal to here m is equal to rho a v1 v is equal to v1, so rho a v1 into v1 square. So hydraulic efficiency is equal to work done per second is the output. Work obtained from the turbine is the output, and the kinetic energy of the jet. So we are obtaining the work from the kinetic energy of the jet. So kinetic energy term is the input and work done per second is the output. Output by input gives efficiency. So rho a v1 into vw1 plus vw2 into u gives the work done per second, and half into rho a v1 into v1 square gives the kinetic energy per second, cancelling out important terms. So the final equation becomes 2 into vw1 plus vw2 into u divided by v1 square. So next we will discuss about how to obtain the maximum efficiency. So what will be the condition for the maximum efficiency? So in order to obtain the condition for the maximum efficiency, we need to check the expressions. So when from the inlet and outlet velocity triangle, we have Vw1 is equal to V1 as we discussed earlier. Vr1 is equal to V1 minus U1. So V1 minus U gives Vr1. So Vw1. So Vw1 term Vw1 term in the efficiency expression becomes V1, and Vw2 terms. Next we are finding the expression for the Vw2 term. So Vw2 So Vw2 is, this is Vw2. How will you obtain Vw2? So Vw2 is equal to Vr2 cos phi minus u2. So we know that Vr2 is equal to K into Vr1. So K into Vr1 cos phi minus u. So also we know that Vr1 is equal to, so from this equation Vr1 is equal to V1 minus u. So K into, instead of Vr1, replacing Vr1 with V1 minus u. So K into V1 minus u cos phi minus u. So substituting the values of Vw1, so this value and this term, that is this is equal to Vw2. So this term and the efficiency equation, we will get the equation as 2 into V1 plus K V1 minus u cos phi minus u into u divided by V1 square is equal to 2 into V1 minus u into 1 plus K cos phi into u by V1 square. If you want to check this expression, you can substitute these values and write it down. Okay. Next, hydraulic efficiency. So the maximum value of hydraulic efficiency. How will you obtain the maximum value of hydraulic efficiency? So the efficiency, if we draw a curve between efficiency and velocity of the wheel. So due to the impingement of the jet, the velocity of wheel increases. If the velocity of the wheel increases, the efficiency also increases like this. And after reaching a certain point, it will decreases efficiency. All efficiency term will decrease after rising to a certain point. So this point is the maximum efficiency point. So slope at this point. So if we take slope at this point, we can take it as, this is a dy du. So slope is normally taken as d eta by du. So at the maximum efficiency point, slope becomes 0. So slope is equal to 0. So the condition for maximum efficiency is d efficiency divided by du is equal to 0. Substituting the value of efficiency. So this efficiency is hydraulic efficiency. So substituting the value. So the expression becomes 2 into V1 minus u 1 plus cos phi u by V1 square is equal to 0. So here one k value is there. It is okay. So the constant values, we need to take the constant values out. So 2 into 1 plus k cos phi by V1 square into d by du into this term V1 into u minus u1 square. So differentiating v1 into u minus u1 square is equal to 0. So this constant value cannot be 0. So this value is not equal to 0 because all the terms have certain values, so it cannot be 0. And so we can assume that d by du into v1 u minus u1 square becomes 0. So if we differentiate this equation, the differentiating the equation, we will obtain as v1 minus 2u is equal to 0. So u is equal to v1 by 2. So u is equal to v1 by 2 is the condition for maximum efficiency. So what does it mean, maximum efficiency? So what does it mean? The velocity of the blade, if the velocity of the blade becomes half the velocity of jet, the velocity of the blade becomes half the velocity of the jet, and then we can obtain the maximum efficiency. So substituting for u, so we have obtained u as v1 by 2. So substituting the value of u in the efficiency equation, hydraulic efficiency equation, we will obtain equation as 1 plus k cos phi by 2. Substituting the values, instead of u we are substituting it as v1 by 2. So v1 by 2 here also, here also. So like that we substitute it and cancelled out important terms, cancelled out the necessary terms, and finally we will obtain the equation as 1 plus k cos phi by 2. So if the friction factor, if the blade is smooth, the k term will become 1. So the equation, maximum hydraulic efficiency equation, becomes 1 plus cos phi by 2. So the maximum efficiency of the Pelton turbine, the equation for maximum efficiency equals 1 plus cos phi by 2. Okay. So that's all for now. This is the expression for maximum efficiency. So in this video we had discussed about the hydraulic turbines, and the first classification of hydraulic turbine is impulse turbine. Second classification is reaction turbine. So impulse turbine, the best example for impulse turbine is Pelton wheel. So we had discussed about the Pelton wheel, and we have derived the equation for the work done efficiency and the condition for maximum efficiency. So this is for now. So thank you.